What is a quantum refrigerator for superconducting qubits? Imagine trying to keep a delicate snowflake from melting in the summer heat. That's similar to what scientists do with superconducting qubits in quantum computers. These tiny circuits need to stay extremely cold to work properly. But even the best refrigerators can't always get them cold enough or reset them quickly. That's where a quantum refrigerator comes in. It's a special device designed to cool superconducting qubits even further, making them more reliable for calculations. Superconducting qubits are the core of many quantum computers. They need temperatures in the millikelvin range, which is just a fraction above absolute zero. Usually, they sit inside dilution refrigerators that cool down to these temperatures. But these refrigerators have limits. They can't always reach the lowest possible temperatures or reset qubits fast enough for large-scale computing. That's why scientists developed quantum refrigerators. They work by using quantum mechanics principles to transfer heat away from the qubits without needing external control all the time. A quantum refrigerator uses 3 superconducting quantum systems called qubits. These are like qubits but with multiple energy levels. One qubit is connected to a hot thermal bath, which supplies energy. Another qubit is connected to a cold bath, where heat is expelled. The third qubit is the superconducting qubit that needs cooling. These 3 systems interact in a special way called 3-body interaction. When they do, energy moves from the hot qubit and the target qubit to the cold qubit. The cold qubit then releases this heat into the cold bath. This process happens automatically, powered by the natural temperature difference between the hot and cold baths. This setup can cool the superconducting qubit down to about 22 millikelvin, which is colder than what standard dilution refrigerators can achieve alone. This extra cooling helps the qubit stay in its lowest energy state, called the ground state, more than 99.97% of the time. That's a big improvement over previous methods, which only reached about 99.80 to 99.92%. The result is fewer errors during quantum calculations and less time spent resetting qubits. Practically, quantum refrigerators make it faster and easier to prepare qubits for computation. They help keep the quantum processor running smoothly and reliably. They also open new doors for studying quantum thermodynamics, how heat and energy behave at the quantum level, using superconducting circuits. These devices could even become part of future quantum processors, making them more efficient and scalable. In simple terms, a quantum refrigerator for superconducting qubits is a tiny, smart cooling machine that uses quantum interactions to make sure qubits are as cold as possible. This helps quantum computers perform better, with fewer mistakes and faster operation. It's a clever way to push the limits of how cold and how precise our quantum devices can get.